So let's focus first on the oxidative stage. Again, if it's oxidative stage, oxidation state of carbon atoms needs to be changed in the course of the process. So this is the starting compound of the whole pathway, and in particular oxidative stage of the pathway, glucose 6-phosphate. And the product of the oxidative stage of the pathway is ribulose 5-phosphate that you can see here. So let's try to see the which carbons change the oxidation state in the course of this process. So we'll have this carbon number 2 of glucose 6-phosphate. It becomes carbon number 1 of ribulose 5-phosphate. And carbon number 1 of glucose 6-phosphate is released as carbon of carbon dioxide molecule. So carbon number 2 in glucose 6-phosphate has an oxidation state of 0, and it becomes plus 1 carbon atom in the structure of ribulose 5-phosphate. So carbon number 2 donates 2 electrons to become plus 1, to turn its oxidation state to plus 1 in the ribulose 5-phosphate. First carbon of glucose 6-phosphate has an oxidation state of plus 1, and it becomes it donates 3 electrons to become carbon dioxide. So overall, there are 4 electrons that needs to be transferred per 1 glucose 6-phosphate molecule, and we know that each NADP plus molecule can accept only 2 electrons at a time, so that's why we need to use 2 molecules of NADP plus per each glucose 6-phosphate molecule, and that brings us to this balanced equation of the oxidative stage. So step 1 of this oxidation stage, again, it's a flux controlling step. It is catalyzed by glucose 6-phosphate dehydrogenases. So dehydrogenases are oxidoreductases. These dehydrogenases will utilize NAD plus as an oxidizing agent, and we will have direct hydride transfer, and actually this proton attached to the anomeric carbon of glucose 6-phosphate will be transferred in the form of the hydride ion. So let's take a look on the mechanism of this reaction. So here we have NAD plus, and we know that in one of its resonance form, the positive charge is assigned to that carbon, and this is where hydride ion would attack. So before hydride can be transferred, we need to deprotonate the hydroxyl group attached to the first carbon of glucose 6-phosphate, and it allows the electrons from this bond to be used to form a pi bond between anomeric carbon and oxygen, and that would release this hydrogen ion so that it can attack the electrophilic center in NADP plus nicotine amide moiety. So as a result, glucose 6-phosphate is converted to this lactone, and NAD plus is reduced to NADPH. So here we have this hydride ion that was transferred. So it's the same hydrogen that used to be attached to the anomeric carbon of glucose 6-phosphate. So the next step will be hydrolysis of lactone, which is cyclic ester, into a cyclic form, into 6-phosphogluconate. The rate of this process is high even for non-enzymatic reaction, but the enzyme 6-phosphogluconolactonase just facilitates it even more. So next step, the last step of the oxidation state, involves another oxidation reduction reaction. So 6-phosphogluconate is actually a beta hydroxy acid, right? So upon deprotonation of the beta hydroxyl group, again, it's possible to form a pi bond, use the electrons to form a pi bond between this oxygen and carbon, and this would release hydride ion, which can attack this position of NAD+, similarly to what we discussed for step 1. So as a result of this process, we form beta keto acid intermediate, and you see how it is kind of shown in those brackets because it's not stable. Beta keto acids are very prone to spontaneous decarboxylation. It readily decarboxylates, as you can see here, and so this second carbon of 6-phosphogluconate becomes the first carbon of the product of oxidative stage, ribulose 5-phosphate. And the first carbon of 6-phosphogluconate releases in the form of CO2. So now we are ready to start isomerization reactions. And here we are going to use two types of isomerases. So ribulose 5-phosphate can be either isomerized into its aldose isomer, ribose 5-phosphate, through the formation of 1,2-ene dialate intermediate, or it can change the configuration at carbon number 3 at this chirality center to become xylulose 5-phosphate. And this epimerization process is catalyzed by this specific epimerase, and it proceeds through the formation of 2,3-indiol intermediate. So here we have 1,2-indiol intermediate. In step 5, we'll have 2,3-indiol